Welcome everyone. We want you to get started by going through and working on the more in-class problem number 1. We'll kind of pop in and out from time to time. The first thing I want you to do is go through and to kind of come up with your list of variables based upon our problem types from our yellow sheet. Then we're going to make a list of our variables that we know from the problem. Then we're going to make our equation, and then we're going to go on and we're going to solve it. So we'll kind of come back and forth. So if you get stuck, kind of pause and unpause as we go. All right, so on this problem, it says a ball is dropped from the top of a 30-meter tall building. How long does it take to hit the ground? There's another question. We're just going to pretend like it doesn't ask that. So right now, we're just looking for numbers. We see the ball was dropped from 30 meters. How long? That's really the stuff we get from the problem itself. Now, I would encourage before, and I'm talking to everyone, not just the camera right now, just for the record. That number is something we're going to put in our list of variable, but I honestly would try to identify as much from problem types first. So if we kind of go through, is this a 1D motion problem? Yes or no? Help me out here. Yes. Yeah, okay. So it's a 1D motion problem. We're in a unit called 1D motion, so yeah, it's going to be. Which one is it? An X column or a Y column? What do we got to make?
Y.
We got to make a Y column. Absolutely. So that Y column is going to look something like this: delta Y, VI, VF, A, and T. Okay? So yes, it was that. Is it a constant velocity? Does it say something where the velocity is constant or the acceleration is 0 or is not? Yes or no? It's a constant velocity problem? No. No, right? No. Okay, so it's not a constant velocity, so this is not true. We can't use that. Is it a special type of problem called a free fall problem, where gravity is the only force acting on the ball? Yeah, it is. Okay, so the ball is dropped, and once that ball is dropped, the only force acting, you can say, what about wind resistance, air resistance? We're going to pretend like that doesn't exist. Oversimplification, I know, but it works pretty well for most situations. So because of that, then we know this to be true. So because it's a free fall problem, we can say my acceleration is negative g, and on Earth, g has a value of negative 9.8 meters per second squared. Negative means direction. It means it's accelerating in the negative direction. I'm going to put a star next to the 4 variables that need a direction associated with it. So if it's going in the positive direction, we don't need it. It's implied as positive. We don't put it. But if it is in the negative, we must put a negative. And if we're talking about the y direction, up is positive, down is negative. So gravity's pulling this thing, causing it to accelerate downwards. That's why we have to have that negative g. Is the object dropped, or does the object fall? Does it say something where it's dropped, or does it say it falls? And it says, yeah, object is dropped. So because of that, we can say our initial velocity is going to be 0. Okay? That's where we're done with problem types as of right now. We'll fill in those other 2 in a little bit. So the question is, how long does it take? So we're solving for final velocity, or we're solving for time if it says how long. We're going to solve for time. 30 meters. Okay, it's going to be dropped 30 meters from a 30-meter tall building. I would encourage pictures. The building is 30 meters tall. From here to here is 30 meters. So if we drop it from the top of the building, how far is the ball going to move? Negative 30, right? It's going to move 30 meters, but because I have that little star, it's a vector quantity, so we need the direction associated with it, and the direction that the ball is going is down. It doesn't ask how high the building is. We're talking about the ball, and the ball is going down negative 30 meters. So for the first part, we don't know final velocity, and we don't care about final velocity yet. That's the follow-up question. So what equation equation number 3. Yep. So go ahead and, if you haven't already, use equation number 3, plug in your numbers, and then solve. Give you 20 seconds more. All right, so that's equation number 3. Notice I have a delta y, because we're talking about y direction, so we substitute. Is equal to VIT plus 1/2 AT squared. Because my VI was 0, I can cancel out VI times T, because 0 times anything is 0. And we get negative 30 is equal to 1/2 negative 9.8 squared, T times T squared. Now I skipped the step in between, but there's a T squared value, then we gotta take the square root, and we gotta determine whether it's the plus or minus. Now, just to remind you, anytime we take the square root of a number, the square root is plus or minus, right? The square root of 4, and I've said this many times, is plus or minus 2. We have to make the choice, is it the plus or is it the minus? With time, it's the plus. If I say on your mark, get set, go, and hit go on the stopwatch, that's time 0. There's nothing before that, right? 0 is the start of time. We can't go negative time. Yeah, but what about, no, that wasn't the time interval we're talking about. So time is scalar. There is no negative number. There is no negative time. Therefore, we're going to choose positive. If it was velocity, then we have to make a choice about up or down. The follow-up question is really just going through and saying, well, now we have the question of how fast is it going as it hits the ground. I don't think we've worked on a problem together in class that has a part B to it. You're asking the second question. I've mentioned it a couple times in videos, but the intent is that, let me rephrase it, the best practice, if you have to solve a problem and then have another problem solved on top of it or afterwards, is to pretend like you didn't just solve for time and then solve for final velocity. The best practice is, because this is not, maybe, I think in this case it is exactly 2.47, but these are rounded numbers sometimes, and to use a rounded number in the next problem is maybe not the best choice. So as often as I can, that's what I'll do in like a sequence of problems. I'll try to make the choice of equation that doesn't have it. So if I were to pick an equation when I did it that didn't have time because I pretended like I didn't just solve for this, I went with equation number 4. And I just want to point out that with equation number 4, you get to this point where the final velocity squared is 588. So when we take the square root, it's plus or minus 24.25. Now the reason it's negative is we have to sign the direction. So we have to ask ourselves, is that object that was being dropped from the top of a 30-meter tall building, was it moving in the positive y direction, which is up, or is it going down? And I hope you realize that if you drop something off of a building, it's going to be going down, so you must assign that negative direction. Try the next one. The next one's similar. There's just a slight variation to this. It says a ball is thrown down at 10 meters per second from the top of a 25.5 meter tall building. How fast is it going when it hits the ground? If you haven't started that one, take a moment to do that. we'll just kind of go through and make sure you're getting this set up, at least in the right process. Okay, so we had a ball was thrown down at 10 meters. So I drew an amazing picture. Oh, okay, maybe not amazing. An acceptable picture of what's going on. So we have an object, a person is throwing a ball down at 10 meters per second, and I took a little artistic, creative license, and I put a bullseye on the bottom. Okay, so is it a 1D motion problem? Sure is. Therefore, we made a column. Why did I use delta y? Because it's moving vertically. So this is a delta y column. Is it a constant acceleration problem? Or I'm sorry, constant velocity problem? The answer is no. Therefore, this is not equal to 0, but we just don't write the number 0 down. Is this the ball? Is the only force acting on the object is gravity? And it depends upon where we're talking about. The way I have my amazing picture drawn, what force is acting on that ball? Gravity. What else? Is my hand pushing on that ball? Is my hand touching that ball? Am I a Jedi? That's a Star Wars reference, just for the record. Okay, and the reason why I say am I a Jedi is because a Jedi can like move things with their hand and their mind, right? Not their hand, with their mind and the midichlorians and all that stuff. But if I take a ball and I throw the ball, once that ball leaves my hand, do my Jedi mind powers make it keep going faster? No, the force is not strong enough. I was never recruited by Obi-Wan Kenobi. Okay, although he was, no, who? Anakin, yeah, that was Obi-Wan, right? I think so. Okay, once that ball leaves my hand, the only force acting on it is gravity. So because of that, now when it was in my hand, was I applying a force? Absolutely. But once it leaves my hand, the only force acting on it is gravity. Therefore, it is a free fall problem. It is a free fall problem. So then we can say the acceleration is negative g, which is negative 9.8. Is it the ball was dropped or a ball falls from the building? And the answer is no. And I'm going to erase this in a second. All that's telling me is it's not equal to 0. That's what that tells me, but you don't want to write that because that's not helpful for solving a problem. I'm just saying you can't write the number 0 there. But what we can say is the ball was thrown initially at 10 meters per second. That we can say. That's what we can pull from problem types. Now, once we determine problem types, we can go back to the problem. And we can say, well, do I know the displacement of the ball? Do I know the final velocity of the ball? Or do I know the time of the ball? And we indirectly know the delta y because we directly know the height of the building. So because the building is 25.5 meters tall, that means the ball is going to go 25.5 meters. So the value, the magnitude of my delta y is 25.5. But remember, these 4 need directions associated with them. Okay, we need directions associated. So this says that my gravity is causing it to accelerate down at negative g, or negative 9.8. This is implying a positive number, which is wrong, right? Which way is this object going? It says in the words, it's being thrown down. So clearly I was doing that on purpose to make sure you guys were paying attention. And you were, because you all yelled at me, so thank you. That must be a negative 10, right? It has to be down, because we throw the ball down at 10 meters. this has to be a negative 10 meters per second. And this must be a negative 25.5 meters, because the ball is going to go down 25.5 meters. Question is asked, I don't even know the question. How fast, how far, how long? How fast is it going when it hits the ground? Okay, so if you got to that, if you didn't have this, there's my question mark, that's what we cross off. Take a minute to choose your equation and then plug it in and solve. Okay, so that's the algebra that I have. I chose equation number 4. Hopefully you did too, because we don't know time and we don't care about time. We plug in our numbers. Remember, a couple key things here. Negative 10 squared is positive 100. I'm not sure. I feel like your calculators get silly sometimes. Yeah, so like on this calculator, if I just go negative 10 and I hit squared, it says it's negative 100. Right? So make sure you take care of that. If that means you got to put things in parentheses, then put things in parentheses. Okay? But that's a positive. Negative 10 squared, negative times a negative is a positive. Same thing here, a negative times a negative is that positive. And then when we go and take the square root, it's plus or minus 24.49. Now, is it the plus or is it the minus? My final velocity has a speed, and I'm going to say speed because speed does not have direction. It has a speed of 24.49. What is the direction that is associated with that speed? Is it up at 24 or down at 24.49? If I throw a ball down, is it magically going to start going upwards after I throw it down? Hopefully not. Okay, so these are fall problems. These type of problems were on your worksheet called Fab 5. We want to add a new type of problem today, actually 2 types. And when we talk about these problem types, what we really are going to talk about is if I take like a ball, okay? And what we can do is we can take a ball and I can throw it in the air, okay? Now, is this a ball is dropped problem? Well, no, it's not, right? Because I'm throwing the ball. Okay, is this the ball is moving through the air and the only force acting on is gravity? It depends on what part we're talking about, right? So if we're talking about in my hand, the answer is no. But once it leaves my hand, what forces, I know we haven't done that unit yet, what forces are acting on that ball? I really like tossing the ball, so I can just keep doing this for a while. Gravity, good. Are there any other forces acting on this ball once it leaves my hand? No. And you can say, what about air resistance? Yeah, a little tiny bit. So we're just going to say no. Okay? So because of that, this ball being thrown into the air and coming back down is a free fall problem. It's not a dropped problem. No, it's not a drop. It's not a thrown downwards. And I want to make that point, I guess. I forgot to make the point. If I take a ball and I throw it down, it's still, should be nice to my new ceiling tiles that they put in this year. Okay? If I take this ball and instead of just dropping it, if I throw it, once it leaves my hand, the only force acting on it is still gravity. This is still a free fall problem. This is still a free fall problem too. The difference between this free fall problem, this free fall problem, and this free fall problem are just kind of the starting conditions of it. The accelerations are the same in all. When we talk about a problem, a ball like this, we often will talk about a special location of the ball's motion. We call that max height, or it's at the apex, right there, right there. Now, how did I know when it was at the highest point? How do we know it's at the highest point? Because it starts to come down, right? It didn't go any higher. It was at the maximum height of the travel, right? And how fast is it going right there? Before, if it's going up, before it can come down, it has to
slow down
until it stops, right? And then it can come back down again. Whew. Stayed on my tiptoes. I didn't know how long I could do that. Okay, so that's our special problem type. The special problem type is, it's called a max height problem. Okay, it's a max height problem. And a max height problem has some conditions, and I can try to zoom in a little bit on that for you guys. A max height problem we know it's a max height problem because it says at max height, or we choose maximum height to be one of our locations. Sometimes it's really beneficial. So this is on our yellow sheet. We're adding that next line to our max height problem. We can choose that max height to be one of our locations. And the reason why that's beneficial is because at max height, we know how fast that object is going. And it's going to be going 0. So if we choose maximum height, we can say, hey, my velocity at that point is 0. Now we got to make some choices. Is that my initial position? Is it my final position? That's something we can deal with. But we know the velocity at maximum height is 0, right? It goes up and it stops and then it comes back down. Now while you're writing that, I want you to think about this. Up 2 points is a free fall problem is when the acceleration due to gravity is negative g, because the only force acting on it is gravity. If we talk about this ball's motion, and we only talk about it on the way up, what force is acting on the ball on the way up once it leaves my hand? What force is acting on this ball on the way up? Oh, yeah, choose max height to be one of your locations. It's not very clearly written, my apologies. So when this ball is going up, what force is acting on the ball once it leaves my hand? Gravity. So because of that, if gravity is the only force, the acceleration is going to be negative g. So that means the acceleration of this ball on the way up is negative g, right? The acceleration of this ball on the way up is negative g because gravity is the only force acting on it. Now, on the way back down, what's the force acting on the ball when it comes back down? me out here. This is going on YouTube, and I'm gonna look like a fool on YouTube, and I'd hate for my kids to, my 8-year-olds, they think like people on YouTube are really cool. So the fact that their dad has a YouTube channel, I mean, that gives me some good cred. Okay? I don't know about street cred. Street cred still a thing? Not really? No? Okay. No? Okay. Well, I don't want my 8-year-olds. So help me out here. This isn't going to be a good YouTube video otherwise. What force is acting on this ball on the way back down? And only gravity, so therefore the acceleration is negative g, negative 9.81 meters per second. Right? We're all okay with that. On the way up, gravity is pulling on us, causes it to accelerate downwards at negative g. On the way back up, or on the way down, the only force acting on it is gravity. Therefore, the acceleration is down at negative 9.8 meters per second squared. We're okay with that? Now, there's this special point called max height right here, and I'm just going to pretend that it stopped and it, like, we're doing like frame by frame, and we just said like pause, and it's at maximum height. And pretend my hand isn't here. What force is acting on this ball? Gravity all of a sudden turns off at max height, right? No, right? Gravity's still acting on this ball at max height, right?
Yes.
Yeah. So what is the acceleration of the ball at max height? Okay, at max height, gravity's still acting on it. It's still the only force acting on it. At max height, the acceleration due to gravity is still negative 9.8 meters per second squared on Earth. And that's a very common mistake that people make when they take a multiple choice question, test question, and they say, what is the acceleration of a ball at maximum height? And they'll say 0, because the velocity is 0. But now I'm going to demonstrate an object that has 0 velocity right now and has no acceleration, and we can watch that object for the next 2 seconds. 1001, 1002. What happened to that object over those 2 seconds? Nothing, right? So if for some reason, on the way up, gravity's pulling it down. On the way down, gravity's pulling it down. But if for some reason at this maximum height, the acceleration was 0, the velocity at its highest point is 0. If the acceleration was also 0, it would hover there forever and ever and ever and ever and ever. And I've only ever had one time in my entire teaching career where I have thrown an object to max height and it didn't come back down. One time ever. It was kind of amazing. I'm going to try to replicate it, but I gave up. You know those water molecules, those magnetic ones that in biology, right? You know what I'm talking about, the red and white, they're magnetic. I just happen to have one laying around, so I was doing that, and I'm just like, oh, maximum height. And one time, I just perfectly, it slowed down, like right as it got to one of the ceiling track tiles, and it went, whoop! And it was amazing, and I celebrated, and I've never been able to do it again. But every other time in my career, it's come back down, because gravity was the only force acting on it. And every other situation in real life is going to be like that. And the reason I'm trying to make that point is, anytime an object is moving freely through the air, anytime an object is moving freely through the air, the acceleration is going to be down at negative 9.8 meters per second squared. Now, when we talk about max height problems, there's 2 different types of max height problems. There's a max height problem, well, I guess there's more than 2. We could say we take this ball and we throw it and we let it do like that. Okay, so we start here and it ends there, but it went up to there in between. Okay, we could say I start it from here and I catch it here. Or we could say, hey, it goes up and it goes to some other place, but I only care about the part up, or I only care about the part coming down. So the nice thing about a max height problem is we can kind of chop that problem into pieces, and we can use from like the toss to the max height, or we can go from max height back down. But one of those choices was where I throw it and I catch it at the same height, and we call that a delta y is equal to 0 problem. And a delta y is equal to 0 problem, remember delta y is the displacement, and displacement is not how far did the ball travel. A delta y, a displacement, is how far is the ball from its starting location, or its starting height in this case. And for these types of problems, there's kind of 2 little things that we can pull from it, or I guess we should start with, how do we know if it's a delta y is equal to 0 problem. And the way we know it's a delta y is equal to 0 problem is the object starts and ends at the same height. Okay, so for example, if I take this ball and I throw it onto the, let me try that again. If I take this ball and I throw it onto the table, okay, and if I'm only looking from when it left the table to when it hit the table, not the throw part, okay, not the bounce part, okay, but if I'm only looking from here to here, it starts here, it ends here, that's a delta y is equal to 0 problem. Okay, if I throw it from here and I catch it right here, that's a delta y is equal to 0 problem. If it starts and ends at the same height. If that is the case, so this ball goes from there to there, it goes from here to here. At maximum height, I know the value. I missed my amazing ball bouncing on the table routine. Okay, so if I bounce this ball and I let it come back down to hit, now let's pretend it goes perfectly straight up and perfectly straight down. Really, it's 2D, but we'll just pretend it doesn't happen. Okay, it goes straight up, and it goes straight back down. If we go from here to here, we know the velocity right here. Now maybe I can calculate the initial velocity here. I know the velocity right here, it's 0. I know the acceleration from here to here is negative g. I can measure this distance, I could calculate this distance, I could time the amount of time. There's things we could pull from those problems, and we could solve for some other variables. And then from here back to there, I know the initial velocity, I know the displacement, I know the acceleration, I can calculate the velocity. And a kind of neat thing, I'm going to say it's neat because I'm a physics teacher. A neat thing is, if the distances are the same, the accelerations are the same, right here, my final velocity on the way up is 0. On here, my initial velocity on the way down is 0. The only thing that happens is my initial velocity and final velocity, they flip. They're the exact same speed, they're just opposite in direction. That means if I take a baseball and I throw it straight up in the air at 10 miles per hour, it's going to hit me in the hand at 10 miles per hour. If I throw it 50 miles per hour straight up in the air, it's going to come back down on me at 50 miles per hour. Okay? But it's in the opposite direction. That's why we say final velocity is equal to the opposite of my final velocity is equal to the opposite of my initial velocity. We're flipping the sign. Now, if we are looking at a delta y is equal to 0, there are times that we've looked at the time, we've calculated, we've only done the max height to maximum height or down from maximum height problem. And if that is the case, we know that time interval to get to max height or to come back down from max height from here to here, let's just pretend is 1 second. It takes 1 second to go from here to there. It takes 1 second to go from here to there. So if we know half the time, the total time is simply doubled. Or if we know the total time and we only want the max height, it's going to be half. Okay? So let's pull out our in-class problem. And let's take a look at in-class problem number 10, I believe it is. In-class problem number 10. In-class problem number 10. So in-class problem number 10 refers to a puck pops out of the floor of a dome hockey game. Dome hockey is, I don't know if it's an arcade game. It's kind of like foosball. There's like this dome over it, and they, instead of like people, like foosball people, there's hockey players with a stick, and you go forward, backwards, and they spin, and the intent of the dome is to keep the puck in there. Generally, it's from the 80s, so I think a lot of the teams on it is Team USA playing the USSR, because the Miracle on Ice had just happened not too long ago. But that's what it's referring to with dome hockey. So a puck pops out of the floor of dome hockey at a velocity of 1.7 meters per second, and it lands on the table. How long was the puck in the air? Then the follow-up question is, how high did the puck go? Okay, so we're only going to look at the first part together. So we have a puck that pops out of the floor, and it can hit the floor again. Okay, it pops up at 1.7 meters per second, and it lands back down. So, let's kind of set this one up. We're gonna kind of work through those problem types on the yellow sheet. Is it a 1D motion problem? Sure it is. Which direction is it? It's in the Y direction. I'm just gonna tell you that because we can move on from there. Okay, it's a 1D motion problem. Is it a constant velocity problem? Does it say something about moving at a constant velocity or acceleration is 0? And the answer is no. It's not one of those type of problems. Is it, the only force acting on it is gravity? Is it a free fall problem? The answer is yeah, it's a free fall problem. So because it's a free fall problem, the only floor hockey puck leaves the table at 1.7 meters per second, reaches max height, and we know that the velocity at max height has a value of 0. Okay, so we know max height has velocity of 0, and then what's gonna happen is that puck is gonna come straight back down and it's gonna hit on the table again. Okay, so it is a it is a free fall problem. It is not a dropped or a falls problem. But because it is a free fall, we know that this is negative 9.8 meters per second squared. Is it a max height problem? Perhaps. Is it a delta y is equal to 0 problem? Well, it starts here and ends here, and I'm gonna say perhaps. You say, well, is it or isn't it? Make up your mind. And well, it depends. We really kind of want to look at the question and figure out what the question is trying to get to. So depending upon what the question is asking, kind of depends on maybe how we want to set this problem up. The question is saying, how long is the puck in the air? And when it says, how long is the puck in the air, what I'm asking for is the total time in the air is what? Now, if we're saying the total time in the air is equal to what, then what we probably would do is, yeah, we'd say, well, let's start here, we'll go up to max height and come back down here because that's the total time in the air. And if that's the case, and that's how we want to set it up, yes, it will be a delta y is equal to 0 problem. Depending upon what the question asks, for example, part B says, how high did the puck go? If we were starting with part D, or part B, then I would probably say, well, I really only care then from here to here, and I'm trying to figure out, well, what was that number? And if that was the case, well, then that is a max height problem. Now from there, I could figure out time to max height, and then if the total time was the follow-up, then I could just double that. But the way this question is kind of ordered, I'm gonna say it's a delta y is equal to 0 problem. Now I will show you, really brief, and I'm gonna erase this in a second. If we wanted to set this up as a max height column, what we would say is my initial velocity, I'm gonna erase this in 30 seconds, because this is for if it was a max height. If this is a max height problem, we would say my initial velocity of that puck was 1.7, my final velocity at max height is 0, and then I could solve for this would be what is the max height, or this would be time to max height. Okay, that's what those things would tell us if we were to solve for them. I am not going to set this problem up as a max height problem. That's where I said I was going to erase that. Because what the question is asking is it's asking for the total time in the air. And if we're looking for a total time in the air, then this would be a delta y is equal to 0 problem. And we haven't proven this in one of the problems we worked through. I worked through in a video for your virtual day. I do this. But if I were to go and I look at my statement for my green sheet or yellow sheet, we know that the puck leaves at 1.7, and according to that yellow sheet, if it's a delta y is equal to 0 problem, then my final velocity is going to be the opposite of my initial velocity. So it's going to go up at positive 1.7, and it will come back down at negative 1.7 meters per second. Hello?
Brought this from food if you want.
Sure,
Key lime pie.
sure.
I'll just leave it right here.
Thank you very much.
Yeah, do you know Mr. What's his name again?
Mr. DeBoer?
Yeah, Mr.
He is
DeBoer.
upstairs in room 333, like straight above us.
Okay.
Thank you very much. So the total time in the air is a delta y is equal to 0 problem. And now what we really have, we have 4 out of 5 variables. And because we have 4 out of our 5 variables, we can really choose almost any equation we want, with the exception of the one that doesn't have time in it. So anything except for equation number 4. But equation number 2, we could say my final velocity is equal to my initial velocity plus a times t. My final velocity is negative 1.7, and I'm going to show you this common algebra mistake. Okay, is people see negative 1.7 and they see a positive 1.7, and they say, well, I got to get the t by itself. I got to get rid of this thing right here. And the common math mistake, and I'm going to erase this is the mistake, is they will say 0 is equal to negative 9.8 times t. And that's wrong. These are opposites. That is a correct statement, but in order to get rid of a positive 1.7, we have to subtract 1.7 from both sides, which makes this negative 3.4. Negative 7 minus 1.7 is negative 3.4, which is equal to negative 9.8 times t. When we go through and we do the algebra for this, I'm going to cheat and just look at what the answer is. We get a time of 0.35 seconds. Now this is the total time in the air. It's the total time in the air. Now the follow-up question is saying, what is the maximum height? That's really what it's saying. This column is not for max height. This is total time in the air. What you'll need to do is you'll have to set up a separate column for max height. And we can say, hey, my initial velocity is still 1.7 meters per second. But at max height, we know this is true. We know the final velocity is 0. We know the acceleration is still going to be negative g, which is equal to negative 9.8 meters per second squared. I want to show you, I'm not going to do this algebra, but I want to show you something quick. And the time here, this is 0.35 divided by 2, right? Because this is our total time, and the time to get to max height is doubled. The time to max from max height is doubled if this is delta y is equal to 0. We're kind of going reverse. Okay, so there's that. I'm not going to take the time to do it. There's 2 problems that I worked through in a video for you to watch. I want to show you this worksheet, your virtual days. You picked up 4 sheets on the way in. We worked on one of them. Those 2 little slips of paper that are progress quizzes, those 2 things get submitted as one of your virtual day assignments. Okay? If we take a look at this worksheet called More Fab 5, I want to point out a few things because people get hung up on some of these. If we look at number 3, how long is Tina the ballerina in the air when she leaps straight up into the air with a speed of 1.8 meters per second? She starts on the floor, she leaps up, she comes back down. It could be a delta y is equal to 0 problem if you so choose. If you take a look at number 5, they did an amazing picture. We have the Earth, we have the Moon. They put a reflector on the Moon during one of the Apollo missions, and they can blast a laser beam at 3 times 10 to the 8th, which is 300 million meters per second. Some people hate scientific notation. There it is for you. The time given is the total time. It takes 2.52 seconds for a laser beam to go from Earth to the Moon and back. Keep that in mind because they're asking how far away are these, not round trip, but one way. The acceleration of a laser is 0. The acceleration of a laser is 0. On the back, number 8, you can cross off part B and part C. Those are unit conversions, and you're going to tell me why a house can't travel 500 miles per hour. Question number 10 is a tougher one. There's two different people. You have Pepe the Clown and Babette the tightrope walker. One jumps off a trampoline, one falls off the tightrope, they catch each other, or one catches the other. Make a separate list for Pepe, make a separate list for Babette. The only thing that they have in common is the amount of time that they're in the air. Okay, that's a tougher problem. Those are some tips, hopefully, for you to kind of help you out along the way. I will probably take pictures of that and post it under today's video too, just so you can kind of get to some of this stuff. This is a homework sheet, as well as the progress quiz. Plus, I worked through 2 in-class problems sheets, and I sent out an announcement saying those 2 problems that I worked through on in-class announcement during the in-class videos. I want you to submit a picture of those 2 completed problems as an assignment as well. Okay, so that's your virtual day stuff. If you have questions, send me a picture, honestly, like, hey, well, what am I doing wrong here? And I can mark it up and I can send it right back. It worked pretty slick the other day. Otherwise, have a good day, everyone.